So in this video I'm going to talk to you about gas laws. In a separate video I'll show you how to do all the different calculations that you need for this unit. This video though is more of an introduction to the basic gas laws as well as filling in some other information that we need that we haven't talked about yet. So the first thing though is looking at the kinetic molecular theory. So there's 5 assumptions that this theory makes. Gas, and we're really just focused on gases for right now. That the particles of a gas have negligible volume. They are in constant motion. When 2 gas particles collide, the collision is elastic, so there's no change in energy. So the amount of kinetic energy that the 2 particles had when they hit is the amount that they leave with. So there's no loss of energy in the collision. If you imagine two pool balls hitting each other, they'll bounce off each other, but they'll actually end up slowing down because some of the energy was lost in the collision. For gas particles though, when things are really, really small, we have slightly different rules for that, so collisions are elastic. There's no intermolecular forces of attraction, so kind of taking a shortcut with IMF there. So one molecule of a gas isn't attracted to another particle. And that the kinetic energy is proportional to the temperature. So this alpha symbol is another shortcut for proportional to. Another way of saying that is as the temperature increases, the amount of kinetic energy that a gas has increases as well. Or excuse me, the gas particles have. So if the temperature decreases, then they actually move with less energy. So apart from maybe the third one, all of those are actually, maybe the third and fourth, all those are actually fairly straightforward, things that you probably would say about a gas if you were asked. So those are the 5 things, and they kind of tie into everything that we're going to talk about now with regards to ideal gas laws and all the different calculations. So some of these will end up in the actual ideal gas law too, so there is some carryover. So let's look at ideal gases. The reason why chemists use ideal gases is because gases can actually be kind of unpredictable and they kind of misbehave, so they don't always follow the rules that we need. So these basic assumptions from the kinetic molecular theory aren't necessarily always true, and there are a couple that definitely aren't true. So negligible volume and intermolecular force of attraction, those are the 2 that are actually easily broken, those 2 rules. But when it comes time to perform calculations using the ideal gas law equation, we actually just assume that there are no intermolecular forces of attraction and that they have 0 volume. So we apply 2 principles from this theory to gases. In reality though, that's not necessarily true, because we know about things like hydrogen bonding, we know about dipole-dipole interactions, and also van der Waals forces. So we know that there's different types of intermolecular forces, so it's very possible that gas particles could be attracted to each other. But having said that, real gases, and obviously real gases have IMFs and also have volume, even if it is really, really small, and this is almost negligible. They do exhibit mostly ideal behavior. But once you get to really, really high temperatures and really, really low temperatures, then those, it doesn't actually work that way. But gases can be tricky to deal with, so it's just helpful just to kind of make some assumptions about them, and those assumptions are that they don't have volume and that they don't have any intermolecular force of attraction. It just helps with calculations and making assumptions about these gases. The reality though can be slightly different, which we'll look at in a second. So those are some basic things that we'll kind of be applying in this unit. So let's get into some more specifics. I'm just going to flip the board. So another thing that we need to know when we're talking about gas laws is the idea of absolute zero, which you may have heard of before. But the definition of absolute zero is when a temperature at which all molecular movement stops. So if you imagine gas particles being frozen, made to such a temperature that they don't actually move anymore, that would be absolute zero. And the theoretical value of that is 0 Kelvin. Should write that out. So, named after the gentleman that came up with the concept of absolute zero, Mr. Kelvin is his name. Anyway, 0 Kelvin is the temperature, the theoretical value that this happens. So there's a really simple conversion between kelvins and degrees Celsius. The reason why we do this is because if you have a negative value in the ideal gas law equation, it can actually leave you with a negative number in your denominator, and that's going to be undefined. So as far as calculations go, it can actually make things really tricky and unpleasant. So if you keep the temperature as a positive value, it makes the calculations a lot more easy to deal with, and it makes a lot more sense too. Because obviously undefined doesn't really help when you're doing a calculation with a real substance like a real gas. So what we do is to convert between kelvins and degrees Celsius, you subtract 273. Another way to think about it, Kelvin temperatures are always a lot bigger, so they'll always be in the hundreds. Well, much bigger. To convert between degrees Celsius and kelvins, then you add 273. So, for example, 298 Kelvin would actually be 25 degrees Celsius. So, we're doing lots of different calculations with gases. The temperatures and pressures could vary. So, one way around that is to assume a standard temperature and pressure. And actually, when measurements of substances get, when properties of substances get measured, we use a standard temperature, a standard pressure, and a few standard other things as well, just to keep the comparisons the same. So we're not comparing apples to oranges. So it'd be pointless to compare a gas at 500 Kelvin and 298 Kelvin because they're going to behave differently if the temperature is different. So when we're looking at substances, we're taking measurements and publishing that in scientific documents, scientific journals, what we actually do is just assume a standard temperature and pressure, and the shortcut for that is STP. So that's not Seattle to Portland, that's standard temperature and pressure. And the temperature that we use is 298 Kelvin, so that's 25 degrees Celsius. And that's usually around room temperature for most rooms, so air-conditioned buildings like this one, roughly around 25 degrees. The pressure that we use is 1 atmosphere. Just to give you a brief explanation on how we end up with that. Pressure, with regards to gases, is force divided by area. Right? So that's how you calculate pressure. So the force for a gas is how it's interacting, how the particles are interacting with each other, how they're colliding with each other, and how those particles are then colliding with the container that they're in. So, for example, a balloon. So the area would be the inside of the balloon. So the pressure that's exerted is force divided by area. The units that we use for force are newtons, and then the units for area are meters squared. So that simplifies to pascals, named after someone called Pascal. It turns out that this value is actually really, really tiny and not that much use. So what we do is use kilopascals, so kilogram, kilo, and kilometer, right? So same sort of idea. This would be, a kilopascal would be 1,000 pascals. And then the pressure that we've measured at sea level, sea level would be 100 kilopascals. And what we do for simplicity is call that 1 atmosphere. Because everything's being measured on Earth, this number could vary slightly, but we use this measurement, either 100 kilopascals or 100,000 pascals, and that's equal to 1 atmosphere. Just to make calculations a lot easier, we'll be dealing with 1 atmosphere, because it just means you deal with 1 when you're in calculations, so actually makes life a little bit easier. So standard temperature and pressure, 298 Kelvin is the temperature, and then 1 atmosphere would be the pressure. Alright, so let's go back and look back at some of the history of gas laws and how we've ended up with this ideal gas law equation that we'll get to in a little while. So there's other people involved. We're going to mainly look at these 3 laws though. So Boyle's law, Charles's law, and Avogadro's law. You've heard of Avogadro before, a gentleman that has the mole named after him, or the number of particles in a mole named after him. That's actually a French name, but it's just easier for me just to say Charles's law, because I don't speak French, and Boyle is just Boyle. So these gentlemen all contributed different things to gases. And what we've actually done is we've taken all this information and kind of condensed it into one easy-to-use, simple equation that makes life a lot easier when dealing with gases. But let's just talk about what these three people contributed, and we will actually use these calculations in a little bit as well. So Boyle, and these are all, this was going back a few hundred years, so gentlemen scientists, members of the aristocracy, doing experiments and mucking around in the rooms or whatever it is that aristocracy do. So Boyle's big contribution was that he found that when he takes the pressure and volume of a gas and multiplies them together, he always gets the same value. So we'll actually look at some data in class, but whatever these two numbers are, you multiply them together, you get the same value. So if that's true, if the pressure and volume equal a certain number when multiplied together, then that must equal the pressure and volume multiplied together for another gas. So what we can actually do is say that the pressure and volume of one gas multiplied together is equal to the pressure and volume of another gas multiplied together. So we can take this equation and solve different problems with it. So if we know the pressure and volume and then one other thing about the other gas, then we can calculate that missing variable. So that's somewhat useful. But this is where that comes from. So when Boyle did these calculations, so there's some caveats to all of these. So pressure and volume. So his assumption was that pressure is constant, so temperature stays the same, and also the number of moles stay the same. So you wouldn't get the same value when you multiply those together if you increased or decreased either of those things, number of moles or the temperature. So Charles's law says that when you take the volume of a gas divided by the temperature, you always get the same value. So similarly, what we can do is, because if this divided by this for any gas is equal to a constant value, always the same value, then we can say that the volume and temperature divided by each other equal that of another gas when divided by each other. So that's actually kind of useful as well. So the story here is again that pressure would be constant. So if the pressure was different, then this wouldn't be true. Also the number of moles, so the amount of gas that you have. Avogadro's law is saying that the volume divided by the number of moles for any gas is always constant, so it's always the same. And temperature and pressure would be constant as well. And we can do the same approach with the values for one gas and the values of another gas, and they're equal to each other. And we can manipulate, move these things around and solve for any one of these four variables. Same for all the others too. Avogadro's law is an interesting one. He's got a big idea. If you imagine these are a couple of balloons all the same size. Oh dear, oh dear. And this has got N2 in it, nitrogen, and that's got H2. They aren't the same size, but imagine they are. And here's a third, say for example, that's O2. If these balloons are all the same size, and let's pretend that they are, even though they're not, let's pretend they are. They've got the same number of moles of gas in each of them. If the temperature and pressure are constant, they're all the same for all three, then the number of particles in each of these would be the same. So that's what I'm trying to draw with that terrible artwork. Anyway, that's Avogadro's big contribution. That's big famous guy, and he got the mole named after him. So anyway, that's the big idea of Avogadro's law. So that looks all well and good. It looks fairly complicated, and all these things are actually interrelated. The pressure, volume, temperature, and number of moles of any gas are all related to each other. And you can look at them separately like this, but it'd be much more helpful if we can put them all together into one equation. And that's what we have now. We have the ideal gas law equation. And that says that the pressure and volume multiplied together are equal to the number of moles, which is N, multiplied by a constant value. And remember that there's constants all the way through here, so if you were to take the pressure and volume, multiply them together, divide by the number of moles, multiplied by temperature, divide these two, you'd always get the same value, so you get a constant value. So So that kind of carries over from there over to here. But this is the ideal gas law equation that we'll be playing around with. So again, P is for pressure, V is for volume, N is for the number of moles, R is a constant. And you'll always, any exam that you take that's a chemistry exam will always have that constant on there for you. It does vary, depending on the different measurements, different units that you use for pressure, it can actually vary quite a lot, but we'll always use the same one. I will show you the others just so you're not freaked out if you ever see them in life beyond my class, but that number does change slightly. But it only changes when the units change for other things. And T is temperature. So ideal gas law. So that's a really important thing to remember. Just checking my notes, I think that's everything. So this was just an intro into where this big equation comes from. It comes from kind of a summary of these things, because these things are all related to each other in some way. But if you're saying, well, you've got to keep temperature constant for one thing and then pressure constant for another, it just creates a big mess. So for simplicity, we have this ideal gas law equation. So a lot of the other things about gases to say are very straightforward. When you heat a gas, it expands. If you increase the pressure, volume expands, and then vice versa. If you increase the number of moles, then the volume increases. Yeah, I think that's it.